Alright, hopefully before you're looking at this example, you've looked at the different types of discontinuities that we have and their various characteristics. You should be familiar with the removable discontinuity, the jump discontinuity, and the infinite discontinuity, which up till now you've always known as vertical asymptote, as those are the kinds of discontinuities that we typically encounter in functions. In example 3 here, we're going to find all the points of discontinuity of the function and identify the types of discontinuities. Now we'll handle this, we'll start out in the same way that we did when we were just looking for asymptotes. So we'll go ahead and take that denominator and set it equal to 0 and solve for x, because that will give us all of our candidates for where discontinuities can exist. And we find that that is at x equals 8 and x equals -2. And then we're going to analyze what happens with the limits as we approach these values from the left and the right to determine what kinds of discontinuities exist. So we need the limit as x approaches 8 from the left of the function, and the limit as x approaches 8 from the right of the function. And we also need the limit as x approaches, that might be the ugliest limit I've ever written, limit as x approaches -2 from the left of the function, and the limit as x approaches -2 from the right of the function. I'm going to go ahead and find these limits numerically. So first I'm going to go ahead and type my function into y equals 3. The quantity x squared minus 3x minus 40 over quantity x squared minus 6x minus 16. And first I'm going to find them at 8. And it looks like the limit as we approach 8 from the left is 1.3, and the same from the right, 1.3. Everybody see that in their table there? Okay. Now we'll do the same thing as we set up our table at -2. And as we approach -2 from the left, it looks like we're approaching negative infinity, and from the right, we're approaching positive infinity. Okay. So there are the places where we have discontinuities. We're going to identify the types of discontinuities that exist. There's an infinite discontinuity, since both of the limits approach either positive or negative infinity. There's an infinite discontinuity at x equals -2. And since both of the limit values approach the same finite value at 8, that is indicative of a removable discontinuity. The limit is finite and exists from both sides, and approaches the same finite value. And when we have removable discontinuities, they actually exist at points. And in this case, it's the point 8, comma, oh no, what's the y coordinate? Well, it's the value of that limit that we found. And so there's a removable discontinuity at 8, comma 1.3. Alright, a couple more examples here. Find a value of a that makes the following function continuous. Well, in order for it to be continuous, we need the limit as x approaches 2 from the left of the function to be the same as the limit as x approaches 2 from the right of the function, which has to be equal to f of 2. Now, f of 2 in this case, since 2 is included, and since linear functions are continuous, f of 2 and the limit as x approaches 2 from the right are going to be the same. And so what we need is we need the limit as x approaches 2 from the left of the left branch of this function to be equal to the value of the function at 2, which is the same in this case as the limit of the right branch. Now, to take the limit of this left branch as we approach from the left, well, it's quadratic, so that means that if I were just looking at the quadratic function in itself, that would be continuous. So the limit on this quadratic is going to be the same as the function value, and so I can just find the limit by substitution. So I substitute 2 in here for x, and that gives me a times 2 squared minus 2 is equal to the right hand side, which is 1. So 4a minus 2 equals 1. 4a equals 3. And therefore, the value of a that makes this function continuous is going to be 3/4. Alright, let's go down to example 4. Find the value of k that makes the following function continuous at x equals 3. Again, we need this value to be the same as the value of the limit of this branch. And so the value of k that's going to make this true is just going to be the limit as x approaches 3 of this function I'm going to go ahead and find this limit. I'm going to go ahead and do it algebraically. This is the limit as x approaches 3. If I tried this by substitution, I would get 0 over 0. So I'm going to go ahead and factor. And I factor both the numerator and the denominator. So this is equal to the limit as x goes to 3 of 2x plus 1 over x minus 7. It's going to be 2 times 3 plus 1 over 3 minus 7. That's going to be 7 over negative 4. And so that's the value of k that's going to make that function continuous. Alright, that ends our lesson on continuity.